In the world of artificial intelligence, size has often been the primary driver of capability. As we push models to larger scales, we encounter a fundamental bottleneck in how information flows through the network. For years, the standard approach has relied on fixed residual connections. These are the pathways that allow information to skip over layers, ensuring that the signal does not vanish as it travels deeper into the architecture. However, as models grow to contain tens of billions of parameters, these fixed pathways begin to show their limitations. The hidden state grows uncontrollably, and the contribution of each individual layer becomes diluted. This is where the Kimi team has introduced a significant shift in architectural design. Their recent research paper, titled Attention Residuals, proposes a radical alternative to the standard summation method. Instead of a fixed weight that simply adds the output of one layer to the next, they replace that static connection with a dynamic mechanism. This new method uses softmax attention over preceding layer outputs. To understand what this means, imagine a conversation in a crowded room. In a standard model, every person speaks at the same volume regardless of what is being said. The noise builds up, and eventually, the signal is lost in the background chatter. In the attention residuals architecture, the system acts like a skilled listener. It selectively attends to the most relevant previous outputs and gates the information flow. This allows the model to decide how much of the previous state to keep and how much new information to integrate at every single step. The motivation behind this change is rooted in the mathematics of gradient flow. When a neural network trains, it adjusts its internal weights based on errors. If the residual path is fixed, the gradients can become unstable as the network deepens. The signal might explode or vanish, making training difficult. By making the residual connection dynamic, the model gains the ability to stabilize these gradients. It creates a more uniform output magnitude and a healthier gradient distribution. This is not just a theoretical improvement. The Kimi team conducted quantitative stress tests to verify the stability of this approach. They focused specifically on scaling scenarios involving 70 billion parameters or more, which is where traditional methods often struggle to maintain convergence speed. The results indicate that integrating this method into the Kimi linear architecture yields significant performance gains. While the specific implementation tested involved a 48 billion parameter model, the stress tests confirmed that the mechanism scales effectively to larger sizes. The key metric here is convergence speed. Models using attention residuals reach their optimal performance faster than those using fixed residuals. They also demonstrate better long reasoning capabilities. This suggests that the model can maintain coherence over longer sequences of thought without losing track of earlier instructions. The dynamic aggregation ensures that important information is not buried by the accumulation of irrelevant data from intermediate layers. However, adding an attention mechanism to every residual connection introduces a computational cost. You cannot simply add more complexity without considering the price. To address this, the researchers proposed a Block AttnRes variant. This optimization partitions the layers and utilizes cache-based pipeline communication. This allows the system to maintain the benefits of the dynamic aggregation without incurring a prohibitive increase in latency. It is a crucial engineering detail because it makes the method viable for real-world deployment. Without this efficiency boost, the theoretical advantages would remain stuck in the realm of academic speculation. By managing the computational overhead, the Kimi team ensures that the method can be applied to large-scale systems without sacrificing inference speed. There is a deeper implication here regarding how we view the transformer architecture. For a long time, we assumed that the residual connection was a static structural element. It was a rule baked into the design, much like a highway on-ramp that always exists. The Attention Residuals paper challenges this assumption. It suggests that the connection itself should be part of the learned representation. This moves us toward a future where depth-wise aggregation is adaptive and data-driven. The model learns not just what to think, but how to pass that thought through its own structure. This shift addresses the issue of outlier-driven instability. In standard models, a single outlier can disrupt the hidden state growth. The attention residuals approach enables the model to selectively gate information flow, effectively filtering out the noise that would otherwise derail the training process. When we look at the broader landscape of machine learning research, this stands out as a unique innovation. Other studies have focused on outlier-driven rescaling or attention sinks, but none have proposed replacing the fixed residual with softmax attention in this specific manner. It is a simple yet high-impact optimization. It does not require complex structural changes to the underlying transformer blocks, yet it enhances expressivity and efficiency. This means that existing models could potentially be upgraded with these changes to improve their stability and performance. It offers a path forward for scaling models beyond the current limits where gradient flow becomes a bottleneck. The quantitative analysis confirms that this is not just a marginal improvement. The stability of the training process is fundamentally altered. The model becomes more robust to the noise inherent in large datasets. This is particularly important for tasks that require deep reasoning, where the model must hold on to information for extended periods. By ensuring more uniform output magnitudes, the system avoids the saturation problems that plague deep networks. The gradient distribution remains healthy, allowing for more efficient learning rates and faster convergence. This creates a feedback loop where better stability leads to better performance, which in turn allows for even larger models to be trained effectively. As we look toward the future of artificial intelligence, the focus is shifting from simply adding more parameters to improving the quality of information flow. The attention residuals approach represents a significant theoretical advancement for adaptive residual pathways. It acknowledges that the path from input to output should not be a rigid structure, but a flexible conduit that adapts to the data. This aligns with the broader goal of making neural networks more interpretable and controllable. If we can control how information propagates, we can control how the model learns. This is a crucial step toward building systems that are not just larger, but smarter and more reliable. The research confirms that this method is a viable solution for the scaling challenges we face today. It offers a way to push the boundaries of what is possible with large language models without sacrificing training stability. As the field continues to evolve, we will likely see more architectures adopting similar adaptive mechanisms. The static residual connection may become a relic of the past, replaced by dynamic pathways that understand the context of the information they carry. This is the direction in which the technology is heading. It is a move toward systems that can manage their own complexity, ensuring that every layer contributes meaningfully to the final result. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.